Hello everybody, and welcome to the final video lecture for 1730 Laboratories. This one goes over experiment 13. As you may have noticed, we have not done experiment 12. With the missing week, we are simply missing a lab. It's okay, however, because labs 13 and labs 12 are quite similar. They both involve standing waves and the speed of sound. Lab 12 involved physical standing waves that you could see in a string. Lab 13 involves standing waves creating resonance that you will hear. As well, 12 involved the speed of sound in a string. This we calculate more rigorously, speed of sound in the air. Do note that speed of sound in the air does change based on temperature. You can see that in equation 1. It has a 0.6 ratio with that temperature. Whenever you are using that temperature, make sure not to use Fahrenheit. We are giving you a Celsius value. Do not convert it into Fahrenheit. So, the general gist of this is we have our little tuning fork, and we have a tube filled with water. So, the concept of a standing wave is that whatever wave is generated and it impacts some sort of a boundary, part of it will be reflected back. Part or all, depending on the setup, will be reflected back. The traveling wave, the incident wave, will then interact with that reflected wave, and they will create a standing wave where at every single point they have an interaction. At certain points, because of this standing wave, which we will be generating at the surface here, you can either have deconstructive or constructive interference. And then based on the measurements we're doing here, we have the resonance points, where we will be doing 1/4 and 3/4 of a wavelength. That is why we have L1 and L2, 1/4 and 3/4. When you take the difference of those two, you get half a wavelength. Then we multiply it by 2, we get the full wavelength. If you need some visual representations of that, I do know that Khan Academy, from what I remember, has some good videos where they show a physical example of standing waves for longitudinal and lateral waves. So, for the first part, we have a tuning fork at key F. Simply going to give it a good whack, and we can measure. And there was a little resonance. I'll make sure it's a little bit more audible. And there's our resonance point. It's around 23.5 to 24.5, and it's range. It simply makes a little bit of a louder sound than everything else. That's the first quarter wavelength. The third quarter wavelength, we can estimate by roughly multiplying the distance by 3. And we can get all the way down here. So, I can't bend cable. We're going to be roughly in the 70s. And there's our resonance point. Roughly 3 times farther below. And that's basically it. For this lab, you would simply you would do multiple sweeping passes. It has you collect the same resonance point to make sure you're accurate. You would create sweeping passes at the first and second resonance points, 1/4 and 3/4, and then you would take the difference, multiply by 2, and then you would move on to the next one. You will then calculate the speed of sound using equation 1, and then calculate the percent error for the theoretical one. And then make sure you use the temperature value we give you. And again, do not convert it to Fahrenheit. Too many students convert it to Fahrenheit for some reason. It's Celsius. Have a nice day.